Since 1992, the United States hasn't detonated a single nuclear weapon. And yet every year, on paper, the U.S. government certifies all 3,700 of them still work. Which raises an awkward question. How do you prove a hydrogen bomb still works without ever setting one off? To answer that, you walk into a windowless building somewhere in New Mexico. For the past hour, every capacitor in the room has been charging. A slow electrical filling monitored by control screens flickering with voltage curves. Nobody stands inside while Z is being charged. If anything goes wrong with that much stored energy, the only sound would be the building exhaling. In the control room next door, the technician calls the count. 3, 2, 1. 26 million amps surge through transmission lines and into a target the size of a spool of thread. A tiny cylinder of copper wires arranged like a miniature fence post. A magnetic field crushes the wires inward in 95 nanoseconds. The wires vaporize into plasma that reaches over 2 billion kelvins, 100 times hotter than the core of the sun. The whole event throws off a 350 terawatt burst of X-rays. You'd think a machine that briefly outshines every power plant on the planet would sound like the apocalypse, but it doesn't. The actual sound when this happens is a muffled thump, like someone closing a heavy door downstairs. What just fired sits inside a building the size of a hockey rink at Sandia. The 26 million amps came from dozens of Mark's generator stacks, each bigger than a refrigerator, each charged to hundreds of thousands of volts, all firing together the instant the trigger is pulled. This is the Z machine, and that thump is the most important sound in American nuclear deterrence. The X-rays it just generated are the same kind a thermonuclear weapon emits in the instant of detonation, just without the weapon. Here's why we built it. Nuclear weapons rot, not the way food rots, but the way precision instruments rot. Tritium decays into helium-3 over years. Plasticizers leak out of the binders. Plutonium pits develop microcracks too small to see. On the day you really need the bomb, the actual fear isn't that it detonates by accident, it's that it does nothing. That last test had a name, Operation Divider. A 20-kiloton device buried 1,500 feet below the desert floor. The mountain shook for 30 seconds. Then it went quiet and never shook again. Bill Clinton signed the Comprehensive Test Ban Treaty in 1996, but the Senate never ratified it, meaning we never legally agreed not to test. We just stopped. Inside the 350 terawatt burst, samples of weapon materials sit on the test rig. Plutonium analogs, depleted uranium, the same lithium deuteride that sits inside the second stage of a hydrogen bomb. Sandia physicists watch how those materials respond, using high-speed X-ray cameras backlit by a laser called Z-beamlit to capture the moment frame by frame. Imagine taking a CT scan of an exploding firework, except the firework is plasma. The explosion lasts 100 nanoseconds, and the camera has to survive the experience. The data feeds the supercomputer simulations that predict every variable inside a nuclear weapon at the moment of detonation. Those simulations are the actual Stockpile certification, and Z exists to tell the simulations whether they're right. Z fires only a few times a year because each shot takes weeks of preparation, a custom-built target, and a small army of physicists. So Sandia built a smaller cousin called Mykonos. It runs at 1 megaamp instead of 26, about a 26th of Z's current, but it can fire several times a day. If Z is the championship game, Mykonos is the practice field. Researchers run tests on Mykonos in days that would take months at the big machine, tweaking experiments before bringing them back for the real shots. Both feed the same goal: model what happens inside a thermonuclear weapon without ever building one. That handles the radiation, but X-rays are the easy part, because before any of it matters, the bomb has to survive everything physics throws at it on the way down: crashes, lightning, cannon fire. And the people whose job it is to break it on purpose are very good at their jobs. The motors ignite. A sled accelerates from 0 to over 600 miles per hour in seconds, throwing a plume of fire and dust visible from 20 miles. The slipper plates that grip the rails turn to shrapnel from friction at supersonic speeds, scattering bits of metal along the track. At a precise point, the sled releases a bomb bolted to its deck. The bomb continues forward in unpowered flight until it slams into a steel and concrete wall built to feel like a high-speed crash. What just fired? Solid fuel rocket motors, same family that powers the second stage of an ICBM, mounted behind a sled riding curved metal pads called slippers along 10,000 feet of perfectly straight rail. This is Sandia's rocket sled track on the eastern edge of Albuquerque. Inside the wreckage, hardened data recorders capture the forces. They tell engineers exactly what every part of the bomb went through during impact. Step 2 is breaking things on purpose. The B-6112 will spend its life strapped to fighter jets, going through crashes and lightning strikes and the kind of stress that would tear most hardware apart. Through all of it, the bomb has to stay safe. If you dropped a 6112 onto concrete from a fighter jet that crashed on landing, would you get a nuclear yield? Sandia's answer better be no. Every time. No exceptions. Down the road from the sled track, 2 cannon barrels fire at the same instant. A mock B-6112 nose assembly rockets out of one end into a 10,000-gallon water tank at an exact speed and angle. A 2,000-pound chunk of metal, a reaction mass, sails the other direction into a padded landing area. The trailer underneath doesn't move at all. That's the Davis gun. 2 barrels, 16-inch bore, same diameter as the main guns on an Iowa-class battleship, bolted end-to-end, 40 feet long total, pointing in exact opposite directions, mounted on a flatbed trailer towed in for the test. The trailer doesn't move because the recoil from one shot cancels the recoil from the other. A normal cannon firing this kind of mass would tear the trailer apart. Inside the splash, the bomb's ground fuse is doing its job. The fuse is the brain that decides when the bomb goes off. On a real strike, the difference between water and rock is the difference between a successful hit and a complete miss. The first impact lasts maybe 3 milliseconds. Inside those 3 milliseconds, the fuse processes accelerometer data 3,000 times. The deceleration curve flattens fast. Water gives way under impact, doesn't bring the bomb to a hard stop. The fuse compares that profile against its program's signature for ground impact, where the deceleration spikes hard and stays high. The signatures don't match. The fuse holds fire. By the time the test article comes to rest at the bottom of the tank, the fire signal has never been sent. The decision was made and locked while the bomb was still in motion. The data tells engineers the fuse read the world correctly. What the engineers don't say out loud. In a real strike, those 3 milliseconds are the entire difference between hitting the right target and a hydrogen bomb going off in the wrong place. The Davis gun was designed in World War I. Sandia rebuilt it for the nuclear stockpile because nothing modern built specifically for this beats it at the job. There's also the drop test. A transport cask containing the test article hoists 30 feet straight up and drops onto a flat surface that won't give an inch, the standard cask certification. Then a separate test drops the same cask 1 meter onto a 6-inch diameter steel spike, built to drive every ounce of impact force into a single point. Both tests, different scenarios, a crane failure, then a collision where something pointy is involved. Neither test is about the bomb itself. Both are about whether the casing breaches and scatters plutonium across an interstate. Some tests at Sandia rarely get talked about. In the geomechanics labs, engineers measure exactly how dirt and rock get pushed around when a warhead punches into them. Because the B-6112 has a ground-penetrating mode, and a bomb that goes off 2 feet underground does something totally different from one that goes off on the surface. The Earth itself becomes part of the weapon. Down the hall, thermal hydraulics rigs track how heat travels through bomb parts in a fire. Because crashes start fires. Fires set off conventional explosives. And conventional explosives can scatter plutonium without ever causing a nuclear yield, which is its own catastrophe. Each of these tests assumes nothing goes right. The plane crashes, the truck rolls, lightning hits the bunker, and through all of it, the bomb survives without ever going off. That proves it survives the journey, but it still hasn't been tested in the most likely scene in nuclear war, a battlefield where other nuclear weapons are detonating around it. At the open end of a 300-foot steel pipe, hundreds of pounds of high explosive go off. The shockwave screams down the tube at supersonic speed. Down at the sealed end, a test article waits. A fuse, a warhead component, a guidance package. mounted near pressure sensors that line the walls every few feet. By the time the wave reaches the article, it has the right shape, intensity, and duration to mimic the blast wave from a nearby nuclear detonation hitting a bomb in flight. High-speed cameras run at 35,000 frames per second to capture how the article responds. This is Sandia's 300-foot blast tube. No other blast simulator in the country can produce a longer pulse or a higher pressure, and it recreates what nuclear war does to its own weapons. Your bomb isn't out there by itself. There are other bombs going off near it, maybe yours, maybe theirs. A re-entry vehicle coming down toward a target might be one of the dozens coming down at the same time. That's the third problem, and it's where engineering gets genuinely clever. Why a tube? In open air, a blast wave spreads out and warps in ways that are almost impossible to predict. Inside a tube, you control the shape and the wave stays clean. Picture an absurdly expensive 300-foot shotgun. Except instead of shot, what comes out is a wall of pressurized air that hits the test piece at supersonic speed. But blast pressure is only half the problem. There's also a radiation half. A nuclear detonation in space, say a defensive interceptor going off near an incoming re-entry vehicle, creates something called a cold X-ray blow-off impulse. The X-rays vaporize a thin skin off the target in microseconds, sending a shock wave punching inward through the warhead. That's not heat or pressure damage, it's the skin literally turning to gas, and it's a totally different physics problem. To recreate that without an actual nuclear weapon, Sandia uses a facility called LIHE, Light-Initiated High Explosives. And here's where things get genuinely weird. A robot arm spray paints the test article with a thin layer of a primary explosive called silver acetylide silver nitrate, SASN, or SASN. The spray process can take 10 hours, depending on the shape. SASN is so light-sensitive that a stray flashlight beam at the wrong wavelength could set off the wet coating before it's ready to test, so the entire booth runs with the lights kept low until they move it. When technicians remotely move the test article into a test cell surrounded by a wall of tungsten wires sealed in quartz tubes, a capacitor bank charged to 40 kilovolts and 208 kilojoules dumps through those wires. All the wires heat white hot in the same instant. The flash hits the entire surface of the test article simultaneously, igniting the SASN at every point at once. The whole layer of explosive flashes off the surface, and the article gets hit with a shock wave that vaporized inward from its own skin. Exactly what cold X-ray ablation does to a real warhead in space. If you've ever wanted proof that scientists are willing to color outside the lines, here it is. Sandia spray-painted explosive on a nuclear weapon and then set it off with a flashbulb. Sandia brought the facility back online in 2025 to put the next generation of warhead, the W87-1, through the same hostile encounter testing. Which is awkward. The W87-1 will spend its operational life on top of a missile that will never face a real defensive interceptor in flight. The only nuclear war this warhead will ever fight is the one Sandia simulates in this room. There's one more piece. Inside a steel cell at Sandia, a small device sits clamped to a fixture wired to dozens of sensors, watched by high-speed cameras at 6 different angles. Behind a containment wall, a charge of high explosive sits at a precisely measured distance from the device. When the charge fires, a calibrated shock wave drives through the device in slow motion, slow enough that engineers can watch every microsecond of the wave's passage and check whether the device still works through the impact. That device is the MK-21 fuse, the brain that fires the W-87 thermonuclear warhead on Minuteman III ICBMs, the switch that decides when the warhead goes off during re-entry. The rig that just delivered the shock is called the Thunderpipe. If the MK-21 ever has to do its job for real, it'll be inside a re-entry vehicle plummeting through the atmosphere at 15,000 miles per hour, while the shock waves from defensive interceptors hammer it from the outside. The Thunderpipe's job is making sure the fuse still works when that happens. That covers blast and radiation, which leaves electronics. Inside a cylindrical cavity at the center of a swimming pool-sized reactor, a B6112 firing circuit board sits next to an MK-21 logic board, both wired into a test harness running diagnostic software. In the control room next door, operators watch dozens of screens, voltage traces, signal integrity, every channel reading normal. Then the reactor pulses, and a flood of high-energy neutrons pours through the cavity at energies that would fry a laptop instantly. Transistors flip bits, diodes degrade, and code corrupts in the middle of running. On the screens, error counts spike, voltage traces ripple. The diagnostic software starts throwing fault codes. The pulse lasts 7 milliseconds. If the electronics survive and still work, they're hardened against everything short of a direct hit. What just generated that pulse? The Annular Core Research Reactor, Sandia's ACRR, sitting in a pool of 14,000 gallons of deionized water a few hundred yards from the blast tube. Day to day, it produces 4 megawatts. When they pulse it, it spikes to 35 gigawatts, 3 times what America's largest commercial nuclear plant puts out, for a fraction of a second. Each facility has thousands of shots and decades of proof behind it. Sandia has tested every piece and every connection on its own. But systems don't fail in isolation. They fail where pieces meet. Now comes the question that matters most. Does it all work together? To answer that question, you do the only test left. Up at Hill Air Force Base in Utah, weapons crews load the Joint Test Assembly into the F-35's internal bay using ground equipment built for the precision required, bolting it to a single hardpoint and connecting it to the aircraft's storage management system through an umbilical cable. From the outside, it looks like any other F-35 on the ramp. The drop site is 600 miles southwest, Tonopah Test Range, 280 square miles of dry lake beds, 160 miles northwest of Las Vegas. It shares a runway with what used to be a secret F-117 Nighthawk facility back when the F-117 was classified. If Area 51 has a sibling, it's Tonopah, and the locals call it Area 52. The pilot runs the pre-flight, engine start, run-up checks, taxis to the runway. Gaining takeoff clearance from Hill Tower, the aircraft lifts off and climbs out southwest into Utah airspace. A chase aircraft joins up at altitude, optical pods rolling and ready to film. The 2 aircraft cross the Nevada border and check in with Tonopah Range Control. By the time they arrive overhead, the range is already hot. Civilian traffic vectored around restricted airspace, instrumentation crews at their stations, the impact zone cleared. Inside the cockpit, the pilot starts working the pre-release checklist. Weapon status, nominal. Master arm, hot. Bay door interlocks, armed. The pilot makes a wide turn and rolls out on the inbound heading, throttling back to release speed. On the ground, watchtowers across the range track the inbound through tracking telescopes, while controllers call out distance and time to release over the radio. Telemetry stations along the dry lake beds lock onto the bomb's transmitters before the bomb has even left the aircraft. High-speed cameras at 3 angles point toward the planned impact point. At the impact zone itself, crews have already pulled back to a safe perimeter. The radio chatter has been steady all morning and starts to thin out. Then everyone settles in to watch. The pilot calls inbound. Range control clears the run. The cockpit displays cycle through the final release sequence as the F-35 approaches the release point. At the release point, the pilot squeezes the pickle button. Yes, the trigger that drops a thermonuclear weapon is officially called the pickle button. Nobody at the Pentagon will tell you why. The bay snaps open. Pneumatic ejectors push the B-6112 down and clear of the airframe. The bay closes within 2 seconds and the F-35's radar signature drops back to stealth. What just dropped? The B-6112, America's only air-delivered thermonuclear gravity bomb. 825 pounds, 12 feet long, with a dial-a-yield warhead that can be set anywhere from 0.3 to 50 kilotons, 3 times that of Hiroshima at the top setting. A guided tail kit gives it accuracy under 30 meters, the same ballpark as a JDAM. It's the backbone of the U.S. air-delivered nuclear stockpile, and the only American nuke certified for the F-35. The pilot banks hard into a safe escape maneuver, accelerating away from the impact zone. Stabilizing fins deploy from the tail kit. The inertial guidance system anchors to the F-35's position at the moment of release. The tail kit imparts a slow spin for stability while the fins begin making hundreds of micro adjustments per second, walking the bomb toward a programmed point on the lakebed below. A retarding parachute deploys behind the bomb, slowing it from supersonic to terminal velocity. The chase plane orbits high, optics locked on the descending warhead against the desert. Range cameras track it down, range telemetry locked. 40 seconds tick by, then 41, then 42. The bomb hits the ground. nothing happens. No explosion, no fireball, no mushroom cloud. Just a column of dust rising slowly off the dry lake bed in the Nevada heat. What just hit was a joint test assembly. Every part identical to a real B-61 except the nuclear core, which got swapped for dummy metal wired with sensors. The whole bomb captured every variable from release to impact. The result isn't a crater, it's a data file. And that data file is what lets the President of the United States look an adversary in the eye and say, with mathematical confidence, that the arsenal works. If you enjoyed this video, then watch this video on how the U.S. test fires intercontinental ballistic missiles. Bye for now.